This is in continuation to our discussion about the general aspects of reaction mechanism. Now we will learn about the determination of reaction mechanism. There are number of ways by which the reaction mechanism can be determined for organic reactions. To list them, we have identification of products, determination of presence of intermediate, the study of catalysis, isotopic labeling, stereochemical evidence, kinetic evidence, and the isotope effect. We shall be discussing each and every method in bit of details, and we start with the identification of products. Now, products is the first outcome of any reaction for that matter, be it organic or inorganic, and it is very important to identify the products formed in a reaction. That is the first basic part of identifying a reaction mechanism too. It is also significant to ascertain the proportion in which each product is formed. We take an example of the halogenation of alkanes, where alkanes are halogenated in presence of light, that is, it is a photochemical reaction, and apparently we see that it gives rise to haloalkanes or alkyl halides. But when the mechanism of this particular reaction is studied, we come to a conclusion that it not only forms alkyl methanes but also gives ethane as one of the products. Therefore, it becomes important to know that not only one product is getting formed, there is another product, and we have to ascertain what is the proportion in which both the products are formed, and this leads to conclusion of the mechanism of this kind of a reaction. So, you may be knowing about the photochemical halogenation of alkanes, by which a homolytic reaction takes place. We get the formation of radicals, chlorine as well as the alkyl radical, which combine to form the alkyl halide, and the two alkyl radicals combine together to give the ethane molecule. Therefore, here not only we are getting the alkyl halide, we are getting ethane and also the formation of a chlorine molecule, which was one of the reagents also. Then it is important to ascertain the presence of intermediate. You would recall intermediates are the species which are formed during the course of a reaction, and the intermediates could be stable as well as partly stable or maybe very unstable. So, depending upon the stability of the intermediates, they could be either isolated or characterized. A number of intermediates have been proposed that could be identified in various ways. So, if we have an intermediate which is relatively stable and the rate of the formation is much faster than that of its consumption, its concentration increases after some time. And when the reaction has reached to a certain extent, the temperature of the reaction is suddenly decreased, or a reagent is added which can stop the reaction. This process is very important and we call it as arresting or quenching of the reaction. This means stopping the reaction in between. The intermediate is isolated from the quenched reaction and is characterized with the help of chemical or spectroscopic methods. This is the case when we say that the concentration of the intermediate is good and it is getting formed during the course of reaction without too much of consumption. But when the formation as well as consumption of the intermediate is very fast, it becomes difficult to isolate it. What do we do then? We detect this intermediate which is not possible to isolate. So, it is possible to get some meaningful information with spectroscopic methods like IR, NMR or some other spectra. For example, detection of free radicals is done by ESR and CID-NP. Both of these are the spectroscopic techniques, the instrumental methods by which one can detect the presence of free radicals as the intermediates in a reaction. Similarly, you may be familiar with the nitration reaction of aromatic compounds. The aromatic compounds undergo nitration in presence of the nitrating mixture, which is sulfuric acid and nitric acid, and form nitronium ion. Nitronium ion is actually the intermediate which is responsible for this electrophilic substitution, and the Raman spectra is used to detect this nitronium ion. So, this is the way we detect intermediates. Another possibility when the intermediate is highly unstable is trapping of the intermediate. That means we are trying to trap the intermediate while it is being formed during the reaction. When the rate of formation and consumption of intermediate is not very fast, it can be trapped during the reaction. This is done by running the reaction in the presence of a compound that is supposed to be reacting with the intermediate in a particular way. We shall take an example here. Benzene is an intermediate, and benzene is actually an unstable intermediate. We have discussed this already. Because of the triple bond present in benzene, it is very unstable. So, the way to identify this intermediate is by trapping, and it is trapped by reacting it with cyclopentadiene, with which it undergoes Diels-Alder reaction. If we look into the reaction, this is benzene with a triple bond, a very unstable intermediate combines with cyclopentadiene. As we can see, this double bond moves here and forms a bond with one of the carbons of benzene, and in turn this carbon attaches itself to this carbon of cyclopentadiene. As a result, the double bond moves to the next bond, and what we get is a Diels-Alder product. If we take another example where benzene is formed by this particular species, this is also established by reacting with naphthalene. Actually, if we see this reaction, the benzene formed will react with another benzene molecule to give us the product, that is two benzene molecules will be combined by the bonds in between, but this benzene actually is trapped by the naphthalene molecule and gives us this adduct, which is again a Diels-Alder product. So, this is the way we can trap the intermediate and can identify it by various means, and spectra is also one of the techniques which can be used here otherwise. Then the other method of identifying intermediates is addition of suspected intermediate. What does this mean? Suspected intermediate is the one where we are suspecting that this could be the intermediate. So, what we say, when an intermediate is expected to be formed in a reaction, then the intermediate is prepared separately and then made to undergo the reaction to obtain the product or the products under similar conditions. What will this conclude? Suppose we get the same compound, formation of the product which we were actually expecting to get confirms the formation of that intermediate during the reaction. If we have got the desired product, it means the suspected intermediate is actually getting formed. This confirms the presence of that particular intermediate. If the desired products are not obtained, it shows that the expected intermediate is not formed. That means the intermediate is not there, therefore, it is not leading to the product which we are expecting to get formed. Therefore, the addition of suspected intermediate in fact gives us a negative evidence. So, formation of the products leads us to the confirmation of that particular intermediate getting formed, and absence of the formation of that product will lead to a negative evidence for that particular intermediate. So, we take an example here. Von Richter arrangement is one of the organic aromatic reactions where beta nitronaphthalene gets rearranged into alpha naphthoic acid. Now, what would one expect here? One would expect that this cyanide would replace this nitro and form an intermediate. This happens to be the suspected intermediate in this case. But is it true? That has to be confirmed. The formation of alpha naphthyl cyanide as an intermediate is ruled out because it does not give alpha naphthoic acid under the reaction conditions which are slated for this particular reaction. So, this is an example which shows that in fact the cyano intermediate is not formed and it undergoes von Richter rearrangement by some other mechanism. Now, study of catalysis is another important method wherein we find out the mechanism. What is catalysis? Catalysis is actually the change in rate of a chemical reaction due to the presence of a catalyst. You know that catalysts are the molecules which themselves do not undergo any change, but then enhance the rate of a reaction. That is how they function. The function of a catalyst is to provide an alternate pathway to the reaction and lower the activation energy with no change in free energy. Now, you know that for any reaction to proceed, it should cross the activation energy barrier. While studying the kinetics and the thermodynamics of reactions, we discussed that activation energy is the barrier which has to be crossed for the reaction to move in the forward direction. Now, this is what the catalyst has a role to play in. The catalyst lowers the activation energy and hence the reaction proceeds to the forward direction. But there may be number of substances that catalyze the reaction or which do not catalyze, or maybe they inhibit also the reaction. So, how do we establish the reaction mechanism? Is the mechanism should be in coherence to the catalyst and the used in the reaction. So, the way we are expecting the catalyst to function, it should be in compliance with that particular mechanism. That is how the catalysis is used to establish a reaction mechanism. Then we have isotopic labeling. You know what isotopes are, and labeling means we are replacing one of the atoms with that particular isotope. The mechanism is studied by isotopically labeled molecules to trace the path of the reaction. We take a very familiar example of the hydrolysis of esters. Esters are the molecules which in presence of water will get hydrolyzed into an acid and an alcohol. Now, there is a possibility of bond breaking in two ways. One is either this CO bond, which is the acyl bond, and another is OR, which happens to be the alkyl oxygen bond. So, we have two bonds which can break, by which either the hydroxy group of water molecule can attack this carbon and give rise to the formation of acid, or the H plus ion from water can attack this oxygen. This oxygen may take the H plus ion, form OH, and hence give rise to the acid and the formation of alcohol. How do we ascertain which bond is broken, acyl oxygen or alkyl oxygen? So, this is established by isotopic labeling, what do we do is we use an isotope of oxygen. Instead of 16O, we use 18O. So, use of H2O18, that is an isotope of oxygen here, explains this. If the acyl oxygen bond breaks, the labeled oxygen will appear in the acid, obviously because OH will be attacking this carbon and RCOH, OH comes from this water, hence what we will get is the labeled oxygen will be present in the acid which is formed during the reaction. Whereas, if it is the OR bond which is breaking, then only H from the water molecule goes to O, hence we will not get the labeled oxygen in the acid molecule. It will rather be in the alcohol group. So, this is what it says, the labeled oxygen will appear in the acid, otherwise it will be in the alcohol. So, this is how we can make use of a isotopic labeling method for the determination of mechanism of this type of organic reaction. Then we have stereochemical evidence. Stereo means in space, that means it is related to the stereochemistry of the molecules. Study of the stereochemistry of reactions and products in many reactions can provide useful information regarding the mechanism. Stereochemistry, may be knowing, is the branch of chemistry which deals with the structure of molecules which differ in their presence of atoms or groups which are differently placed in space. So, the bonds remain the same, the bondings, and everything, the structure remains the same, but in space they are placed differently if we view their three-dimensional structure. If we take an example, in this case, SN1 reaction proceeds with the formation of a racemic product. Now, because stereochemical compounds would be showing either configurational or conformational isomerism. In configurational, we have one optical isomerism. So, it is related to the optical activity of the molecules. And as you would read in your further discussions, that nucleophilic substitution reactions are the ones which exhaustively make use of this stereochemistry, and in fact the stereochemical evidence becomes very important in deciding whether the reaction is proceeding by SN1 or an SN2 mechanism. In case of SN1 mechanism, for example, this particular halide will undergo reaction and give a racemic product. What is a racemic product? A racemic product is a mixture of two optical isomers. If we have 50% of D, we will have 50% of the L isomer, and the optical activity by means of having equal amounts of both the isomers becomes 0. We call such isomers as the racemic product. This is what is depicted by a SN1 reaction. Whereas in case of SN2, we get inversion of configuration. Similarly, when there is possibility of the product existing in two stereochemical forms, formation of a specific isomer takes place. So, we take an example of formation of chlorosuccinic acid from malic acid. Chlorosuccinic acid exists in two isomeric forms, plus, minus and plus enantiomers, and the minus enantiomer is obtained when malic acid is treated with PCl5, and the plus isomer is obtained when it is heated with SOCl2. Though it may appear that the two similar appearing reactions may not form similar products. Therefore, predictions for either reactions like additions, eliminations and rearrangements are also done on the basis of stereochemical studies. Now, there are two important aspects which are related to the stereochemical evidence, and these are stereospecific reactions, which are the reactions where the stereoisomeric starting materials give stereoisomerically different products under the same reaction conditions, and these are called as stereospecific reactions. So what happens? The two stereoisomers, if put under the same conditions, will give two different stereoisomers, which will mean one isomer will be specific to the one product, which will be an isomer of the other product obtained by the other isomeric form. We take an example of bromination of alkenes. So, addition of bromine to trans 2-butene yields exclusively the meso product, while a DL pair is formed from cis 2-butene. We saw earlier that D and L are the two active isomeric forms of one compound, whereas meso product is the one which has an optical activity of 0. So, the trans alkene will give rise to specifically the meso product, which by virtue of its internal cancellation of optical activity will give rise to a meso product, and the cis isomer will give rise to optically active isomers, the DL pair. So, one is D, another is L. In case of SN2 reactions, there is always an inversion of configuration. As a result, here again we observe stereospecificity. So, if we are starting with R isomer of this particular molecule, we will get the S product. There will be an inversion of configuration, and whenever there is an inversion of configuration and a different optical activity is observed, we say that this particular reaction has undergone SN2 mechanism, whereas we saw in the earlier case SN1 reaction proceeds with the racemization of the products. The other type of reaction is stereoselective. A reactant has the ability of forming two or more stereoisomeric products in a particular reaction, but one is formed preferentially. So, here we have an example of 2-iodoalkane, which gives rise to, on elimination, the different alkenes. As we can see here, the maximum percent of the alkene is the one which is obtained in its trans isomeric form. The cis isomer is formed in only 20% of the amount, whereas the one which is unsubstituted is also obtained in small amounts. So, this reaction is called stereoselective because we are starting with this particular reactant and it has the ability to form more than one isomer, but preferentially the most stable gets formed in the maximum amounts. Kinetic evidence is another method by which we come to the identification of a reaction mechanism, and you know that kinetics of a reaction is related to the speed or the rate of a reaction. The speed and the rate of the reaction also depends upon the concentration of the reactants and products. And you would know it very well that with time the concentration of reactants keeps decreasing and the concentration of products obviously will keep increasing. How the rate varies with the concentration gives the information about the mechanism. Generally, the rate is proportional to the concentration of reactants, and the concentration of the reactants decreases with time, as we have said. However, the rate does not depend always on the concentration of all the reactants. See, we saw in case of SN1 reaction, that is nucleophilic substitutions which are unimolecular, have only the reactant concentration which matters during the rate of the reaction when it comes to deciding the rate of the reaction. Whereas in case of SN2, that is substitution nucleophilic bimolecular, we have the rate depending on both the substrate and the reagent. The kinetic studies give the information of the order of a reaction, which gives an information about how many molecules take part in the rate determining step. Then we have rate constant, effect of change in the structure of reactants, in solvent, the ionic strength, the addition of catalyst, etc. on the rate indicates important information about the mechanism. And if we plot a graph of long k with the inverse of temperature, we would get a linear relationship, which also gives a good idea of the mechanism of the reaction. And this is, of course, we call as the Arrhenius plots, which you would study in your other discussions. The last is the isotope effect. Isotope effect is very important, as these are observed when one of the atoms, particularly the hydrogen atom in the molecule, is replaced by its heavier isotope, that is deuterium. And it is not necessarily that we have only hydrogen isotope which matters here. There are number of other isotopes, for example the isotope of carbon, oxygen, etc., which are important for isotopes effect studies. And this is called, when we are using deuterium, we call it as the deuterium isotope effect, obviously, and expressed by the ratio of Kh by Kd. It is the rate constant when we have hydrogen, and divided by the rate constant when we are using deuterium in place of hydrogen. The Cd bond being stronger requires more energy to break as compared to the Ch bond. And this gives an important information about the mechanisms when rate determining step involves breaking of CH bond. We shall see how. There are two important aspects to it. One is primary isotope effect. If the magnitude of the kinetic isotope effect, that is Kh by Kd, is 2 or more, it suggests that CH bond is breaking in the rate determining step and referred to as the primary isotope effect. The effect in the following reaction at 350 K is as high as 4.6, and as you can see, this is a halogenation reaction wherein we have replaced this, the isotope of this hydrogen is used, and this clearly shows that in the rate determining step, this CH bond or the CD bond is the one which is breaking and showing a primary isotope effect. The other effect is secondary isotope effect, which is relatively small. The Kh by Kd is to the tune of 0.7 to 1.5, and we call it, of course, as the secondary isotope effect. And these arise when the substituted hydrogen atom is not directly involved in the reaction, that is the CH or the CD bond is not breaking in the rate determining step. And there is an example where this halide is being treated with water and giving us alcohol. It clearly shows that the Kh by Kd is only 1.34. That means the CD bond or the CH bond is not involved in the rate determining step. Let us summarize what all we discussed in this particular lecture. We talked about the determination of reaction mechanism. The various methods used are identification of products, determination of presence of intermediate, the study of catalysis, isotopic labeling, stereochemical evidence, kinetic evidence, and isotope effect. And what we gather from learning all the various methods is that once we know any details of these aspects, we will be able to rationalize a mechanism of the given organic reaction. Thank you.